welcome to our final exam review. So we're going to go through a series of questions and see, just make sure you're ready for the final. Number one, list three or more terms that complete the pattern in each of the following. Explain your reasoning and tell whether each sequence is arithmetic, geometric, or neither. Okay, so first task is to just notice what we have here, see if we can figure out the pattern, and then decide if it's an adding pattern or a multiply pattern. So if I go from 1 to 2, I clearly added 1. If I go from 2 to 3, I added 1. 3 to 5, I'm adding 2. Oh, wait a second. 3 to 5, I'm adding 3. 8 to 13, I added 5. So I'm not adding a constant amount each time. I'm adding a changing amount, but do you notice the 1, 1, 2, 3, 5? That's actually the previous numbers. Okay, so it looks like what I'm doing is I'm adding the previous number to get to the next number. So let's see. Is that right? Let's see. So 1. So here I did. So there's a number missing that we don't get to see. But looks like when I get to 3, I added 1. To get to 5, I added 2 back. To get to 8, I added 2 back. So I'm adding 2 from the previous position. So to get to 13, I add 5. So it seems like in this next position, I need to add 8 to the 13, which puts me at 21. So added 8 there. And then I need to add 13, which is 34. And then I need to add 21, which is 55. Okay. So even though this pattern was an adding pattern, this is not considered arithmetic because an arithmetic sequence is one where it's constantly being added the same amount each time. So since we're adding changing amounts, then this would be an example of neither. And the reason is we're adding different amounts each time. Okay, then we go to the next one, which is 1, 4, 16, 64. So we're going to try looking at it through adding i's. So if I add 3 and I add 12, okay, so I'm already not adding the same amount. Okay, so let's try multiplying. So times 4, 1 times 4 is 4. 4 times 4 is 16. Okay, so now that we got it. Okay, so I am multiplying by 4 each time. So I'm going to pull out a calculator here. So 64 times 4 is 256, and 256 times 4 is 1,024, and then 1,024 times 4 is 4,096. So clearly we are multiplying, and so multiplying by the same number is called a geometric pattern, and the rationale is that we are multiplying by 4 each time. Okay, and that brings me to the last pattern. So 0 to 4, let's see, so let's try adding 4, 4 to 8, add 4, 8 to 12. Okay, so we're adding 4 each time. So if I add 4 to 12, I get 16, then 20 and 24. Okay, so this definitely is arithmetic. And we are adding 4 each time. In number 2, we are asked to find the sum of a long list of numbers. The intention is not to add a bunch of numbers in the calculator. That would just take forever. So this is a pattern that we looked at where I'm going to take the 51 to 151 and I'm going to repeat it in reverse order. So 151 plus 150 plus 149 plus ... all the way down to 51. Okay, now if I take that entire list and I add the two lists together, I should get 202 plus 202 plus, okay, so I've got a big long list of all these 202s. But the question is, how many 202s do I have? And then this is where the common misunderstanding that I see students have, because a lot of times they'll just go 151 minus 51, say it's 100, so clearly I have to have 100 numbers. And I want to caution you that you don't want to do that. There is a formula that tells us the nth term of an arithmetic sequence. It's the nth term is the first term times n minus 1 times the common difference. Okay, this is, so I'm going to box this. There's a few formulas that I expect you to know going into this test, and this is one of them. Okay, now what I'm going to do is I'm going to input all of my information and work backwards to solve for n, just to show you that you want to be careful. It's not 100 like you think it is. Okay, so my nth number in this pattern is 151. My first number is 51 plus n minus 1. That's what I'm trying to find, is n. And my common difference is what do I add each time to get the next number in the pattern, and I'm adding 1. Okay, so now I'm going to subtract, and that works out fine. So if I subtract, I get 151 minus 51 equals n minus 1. So here I get 100 equals n minus 1. So then n has to be 101. So this is that mistake that students make that they overlook. That if you simply, and it only works this way because we're adding 1 each time, the pattern is going to change, obviously, for the test. But there are 101 numbers when I start at 51 and I end at 151. So when I come down here and I look at that 202, how many 202s are there? There's 101 of them. But that would be twice as much as I want. So because remember I added 51 to 1 plus 151, I added it twice, the 2 times that I added it. So I want to take that product and divide by 2. So 202 times 101 divided by 2 is 10,201. So that sum adds up to 10,201. Number 3, we have an example of an application problem. So the first part is to read it and then make sure we understand what it's asking for us, from us, and then we have to make a decision about what formula or operation would make the most sense. So here we go. I'm going to read it and sort of underline or highlight the important pieces. 3 pieces of wood are needed for a project. They are cut from a 90 centimeter long piece of wood. The longest piece is, is an important math word, 3 times as long as the middle-sized piece, and the shortest is to be 10 centimeters shorter than the middle. Okay, how long are the pieces? Okay, so we have a long piece, a middle piece, and a short piece. Alright, so what do we know? We know that the longest is 3 times the middle piece, so that's 3 times the middle, and the shortest is 10 centimeters shorter than the middle. So the middle minus 10, so the middle apparently is just the middle, since everything else happens to be in terms of it. Well, what do we know about those 3 things? Those 3 things have to add up to 90. So I'm going to set up an equation, and then I'm just going to solve. So 3m plus m is 5m minus 10 equals 90. So here we'll add 10 to both sides, so we get 5m equals 100. And so what is m? m is 20. So how long are the pieces? So coming back in here, if m is 20, then 3m, so 3 times 20 would be 60, and 20 minus 10 would be 10. So the 3 pieces are 60, 20, and 10. And there's the math that backs that up. Number 4, write 256 in each of the following bases. Okay, so we're going to convert the number into another base. Right now it's in base 10. So what I want to do is I want to think about, let's see, so 8 to the 0th power times something plus 8 to the 1st times something. I just realized I need more space to write. Okay, so 8 to the 0 times something, 8 to the first times something, 8 squared. Okay, now I'm not sure if I need to go all the way up to 8 cubed or not. Let me, let's actually take a look at that. 8 cubed is 512. So 8 cubed is actually too big. Kind of right off to the side here. So we got 8 to the 0, which is 1. 8 to the first is 8. 8 squared is 64. 8 cubed is 512. Okay. So I don't need, so in other words, I can't put 8 cubed in this pattern so far, but I'm going to start with 8 squared equals 64. So what I want to know is how many times does 64 go into 256, and in particular, what's the remainder? So if I type that in, I get 4. So it goes in there 4 times evenly, and that means that there is no 8 to the first and there's no 8 to the 0th power. Okay, so that means 256 translates to 400 in base 8. All right, base 11. So same idea. I want to figure out a couple powers of 11 here. Now I know 11 squared is 121. So I know 11 cubed is going to be too big. Okay, so 256 over 11 squared. All right, I get 2 with a remainder of, so 256 minus 2 times 121, the remainder of 14. Okay, so there's a 2 there. And so I want to go to the remainder, and 11 goes into 14 once, with a remainder of 3. And so 3 over 11 to the 0th power is just 3, which is what's going to happen every time. So in base 11, that's 213 for that one. Number 5, we're given a set, we're given set notation. So this idea of numeration, N-U-M-E-R-A-T-I-O-N, is our universal set. And then we've got some subsets based on that. And so we're going to answer some set notation questions based off our set. For starters, we're going to look at B union C. So if I look at B and I union everything with B with everything in C, I'm going to get a set of letters. So obviously everything from B gets to come over. And then I'm going to add on to it anything else that C has in it that B doesn't. So the R is there. We already have the A. We already have the T. I don't have an I yet, so I'm going to add that. I don't have an O. I don't have an N. Okay, so that's the union of B and C together. So it's everything in B, and then add on top of it everything in C, and there's no reason to put repeats. The next question, intersection. So A intersect B is to look at what do they have in common. So now I'm looking at the overlaps. So I'm going to start with A, set A. Set A has A, T, and E in it. And I can see that A is in both. I can see that T is in both. And I can see that E is in both. Okay, so just so happens that all of A is a subset, a proper subset of B. Next up is the complement of C. So complement means go to the universal set and look for things that in the universal that aren't in C. So for example, I see an N, so that means N's in C, so I can't, the opposite of N, that sounds strange, the opposite of N. So since N is in C, then I'm not going to put it in as complement. U, however, is not in C. M is not in C. E is not in C. R is, A is, T is, I is, O, and N is. Okay. So I've got 3 elements that are not in C. Everything else happens to be in C. So that's what it's asking. And then D is asking about the the cardinality of set B. Cardinality is just a fancy way of saying how many elements are in B itself. So I'm just going to go count the number of elements, and it's TAME. So there are 4 elements in B. So the cardinality of set B is 4. All right. Classify the following as true or false. So there's going to be some set vocabulary, and just going to make sure we understand what on earth it means and how, obviously answer the question. The empty set is a proper subset of every set. That actually is 100% true. Let me kind of clarify what it's saying. Let me go up here and I'm just going to pick a set. Let's look at set A, for example. Well, if I want to write every subset that could possibly exist, right? I could do A, I could do T, so I could do elements of 1. I could do elements of 2, so AT, AE, and TE. I could do all 3 elements, A, T, and E, or I could do none of the elements, so the empty set. So all of those would be considered subsets of ATE. Actually, all except ATE would be considered a proper subset. Proper subset simply means that there are more elements that I know of other than AT and E. So AT and E is the set, so I can't say that there's more than that in there. Anyways, going back to this question, the empty set is a proper subset of every set. Yes, that is true. B, for all finite sets A and B. Okay, that actually matters, that word finite. If the intersection of A and B is not empty, okay, so if, I'm going to go off to the side here. So I have set A and I have set B, and I am talking about this overlap here. So that's the intersection of that, and I'm told that there's something in it. So there is some element, some letter, some number, something that overlaps between the two sets. Okay. And the word finite simply means that there is a countable number of objects in A and a countable number of objects in B, which also tells me then that there's got to be a countable number of objects in the intersection. Okay. So then the question reads, then the cardinality, or the number of elements in the union of A and B, is equal to the number of elements in A plus the number of elements in B. Well, I think this one's a little bit easier to illustrate with some actual numbers. So let me actually make up some sets that fit this criteria. Actually, let's come up here. No, I'll just make up one. I was going to use the original sets that we had up there, but let's just do 1, 2, and 3. It's clearly a finite set. And let's do 3, 4, 5, and 6. Okay, so I need to have an overlap of some type between them, and I can see that the number 3 is in both sets. Okay, so let's look at A union B, which would be 1, 2, 3, 4, 5, and 6. Okay, so the cardinality of A union B in my little made-up set are 6. There's 6 elements in there. And the cardinality of A is 3, and the cardinality of B is 4. So, according to my little statement here, telling me that there's something in between the intersection, does that mean if I add up all the elements in A union B, I should get the number of elements of A plus the number of elements of B? Well, does 6 equal 3 plus 4? Nope, that's false. So that's a false statement. And all I needed to know in order to make that false is that there was a non-empty intersection. All right, then last but not least, on this one, the set 2, 4, 6, 8, 10 is a infinite set. That actually is true. Infinite means it goes on forever. There's a repeating pattern to it. So that is a true statement. Okay, so just a word of caution on this. On the review, I picked these questions, so these obviously are not going to be on the final, but you want to go back and review set notation, vocab, properties of sets, and just make sure you're comfortable with describing these things. Notice on A and B, I went and I drew a picture, or at least went back and looked at some examples. So you need to be to a point with the vocab that you can describe the examples and illustrate why something is true or false. Anyways, good luck on that.